All here.
And you can take it away.
All right. Well, I am absolutely delighted to have our first speaker of the 2023-2024 season for NASA Galaxies Science Interest Group. Jason Tumlinson from Space Telescope about the HabWorlds and what you can do about it, which is absolutely what we want to talk about this coming year. So without further ado, Jason, do you want to take it away?
Benny, can you give a
Sorry,
quick spill of who we are? Like, what is the Galaxy SIG? Just in case people are not.
Yeah, I'd like to know that myself.
I'm sorry for rushing. I rushed over here, so that's why I'm in a rush mode. So the NASA established for the science interest group, several science interest groups to identify and define what kind of science we will be doing with the next series of great observatories. There's a STARS one, there's an AGN one, there's several others. And we are me and Aaron are leading the Galaxy, so extragalactic, but broadly defined interest group. So we can talk about what kind of things need to happen in order for us to maximize our use of things like the Habitable Worlds Observatory or the other great observatories, and what gaps exist. So what catalog do you need? What kind of models would you need in order to maximize your science there? We've been established about a year ago proper, and this is our seminar series. And sorry, yeah, I rushed over here. Sorry. So we're delighted to have this series of talks. Will still happen every Tuesday in the fall semester and every Wednesday at 1 p.m. Eastern Standard during the spring semester. Let's see, we have a website at the NASA. Sorry, I can't get the acronym. And please sign up for the email list so that we can reach you all for the next one. This will be the Zoom link for it, and we have a full docket for this coming year. Was that it, Aaron? Do you have anything to supplement with? Because my brain is still.
No worries. Thank you for giving that quick spiel. So just a quick housekeeping thing. Please stay muted throughout the talk and save questions and discussions to the end. Jason's talk won't take up the full hour, so hopefully we'll introduce some discussions at the end. So yeah, stay to the end.
Okay.
Okay, shall we?
Go ahead, take it away.
Okay, so as you were just informed, I'm Jason Tumlinson. I'm an astronomer here at Space Telescope Science Institute and research faculty across the street at Johns Hopkins. I was invited to talk to you today because I've been working on the HabWorlds mission in some capacity for a long time. It's in its previous instantiations as LUVOIR or HDST or At Last. So I have some memory of how we got here. But also, over the last few months, I spent a lot of my time planning for a conference that we had here in Baltimore in July, Science with the Habitable Worlds Observatory and Beyond, which was turned out to be a fantastic set of science talks and technology and programmatics and international involvement and a whole bunch of things. So what I'm going to do today is draw on some of the highlights of this meeting to tell you about some of the most exciting science ideas. It will definitely have a focus on galaxies as the science goals, to the not exclusion, but to the de-emphasis of most of the other things. But of course, there's a huge range of science to be addressed with this observatory. If you'd like to look at the archive of talks, that QR code there will take you directly to the Institute's webcast archive, where you can view all these things in your leisure. So how did we get here? It's common practice. It's now well-established practice for the United States government agencies that support and fund astrophysics to do decadal surveys through the national academies every 10 years. And every 10 years, there has been a recommendation for a flagship observatory of one kind or another. Going back to the 1970s, which led ultimately to Hubble launching in 1990, then through Chandra, Spitzer. Those three made up the old great observatories, or in those days, they just called them the great observatories. And then the 2001 recommendation was for Webb, which we finally got off the ground 20 years later. Roman in 2011, and this time around in 2021, Astro2020 recommended a new fleet of great observatories modeled after the old, which would be a combination of UV optical and infrared, X-ray, and far infrared observatories. So a lot of what we're aiming at now is building out this fleet over the next few decades, where HabWorlds is really only the first of these missions to be developed and hopefully get to the launch pad. But the goal of everybody involved is to ultimately enjoy another fleet like we've had in the past, where so much science is getting done simultaneously. Of course, science always leads this exercise. You have to put the science first if you're going to decide what kinds of missions to build, what kinds of facilities to build. The Astro2020 survey broke the science down into three major elements: worlds and suns in context, that's sort of exoplanets, life on exoplanets, and those things in their proper astrophysical context. New messengers and new physics, which has to do with particle detections, particle astrophysics, non-photon bearing messengers, so gravity waves, particles, neutrinos, things like that. And cosmic ecosystems, which is a real buzzy buzzword for all the complicated stuff that happens when galaxies and stars form in reality. So HabWorlds is the top recommendation to boil it all the way down to its minimal properties. It's a segmented 6 to 8 meter primary mirror with a coronagraph, which allows detection, or rather search, of 100 nearby star systems for Earth-like planets and characterization of their atmospheres. And I'll show what that looks like in a minute. And this is the key point, that exoplanet science case is coupled to a transformative astrophysics portfolio that provides the observatory part of the name. So we have habitable worlds on the one hand, searching 100 hab zones in the nearby galaxy, and observatory is supporting the idea of transformative astrophysics. This is a little movie, which is a photon-based, trying to be as accurate as possible, simulation of what our solar system would look like if you put it at 10 parsecs and then observed it with a HabWorlds-like instrument. So the first thing you notice here is that the sun is missing, but you can see the planets. So let me let this flow for just a minute. This is, as I say, a simulation which is actually pushing photons through the model of the coronagraph. There's Venus and Earth. Jupiter and Saturn were labeled a little earlier. Mars, sorry, man, you're just not bright enough to see, really. Maybe if we're lucky. But this is very much what the observation will look like when we're searching 100 habitable zones for Earth-like planets. Little faint smudges. But it's very important to note that these little faint smudges, especially for Venus and Earth, they're about 10 to the 10 times fainter than the star, which is why we have to do so much work to delete the star. We're basically taking 10 billion photons out of the beam for every one that we leave in the star, and that allows us to see the planets orbiting their sun. So that really is the science case for the habitable worlds part of the observatory. Of course, it's not just taking a picture that provides all the value. In fact, I would say that as a spectroscopist, a spectrum is worth 1,000 pictures. So what you need to be able to do is take a spectrum of each of these candidate Earths and measure its atmospheric composition, looking for signs that there is metabolism, that there's life there. And the problem we face, which is also an opportunity, is that the Earth's modern atmosphere doesn't look anything like it did 1 billion years ago, or 2 or 3 or 4 billion years ago. The atmosphere of the Earth has evolved substantially over the course of life on Earth. So even though we kind of know what to look for by inferring the Earth's prior atmospheric composition from geology and other things like that, really it's wide open, and we could see any combination of many different things. So spectroscopy at the 10 to the minus 10 contrast level is the killer app for the exoplanets case for HabWorlds. This is what we're trying to do, detect those signs of life on exo-orbits. And that really drives the size and performance of the telescope. So, you know, it's amazing to me that when I was a kid in school in the 80s, you know, I learned, of course, like we all did, that Copernicus and Darwin had removed humans from the center of the universe. And my kids are learning in 6th grade and 10th grade now that, you know, there's planets orbiting these other stars. But it's pretty amazing, the prospect that, you know, not too long from now, our kids might be taught in school that not only is there life on some other world, but we will be able to go out and point to the star where that planet is orbiting. So to me, as an astronomer who does theoretical astrophysics of galaxies, this is still a very compelling science case at a human level, and really justifies a lot of what we're trying to do. But of course, that's not why we're here today. We are here to talk about galaxies. I apologize, I'm having a little bit of trouble with my slide transitions, so we may have some lag in the visualizations. At some points, I may have to drop out. So, as I said, one of the three key drivers of science in the 2020s from Astro2020 is cosmic ecosystems. And within the cosmic ecosystems science theme, the priority area, the area that the survey regarded as the most compelling for new investments, is what they labeled unveiling the drivers of galaxy growth. So that's accretion onto galaxies, feedback that energetically affects their environment, the formation of supermassive black holes and their effects on their galaxies, the evolution of dust in the far infrared, which is a key driver of the chemistry of cooling and molecule formation and star formation. So this is a very, very, very broad scientific domain, even if you've narrowed the whole survey down to unveiling the drivers of galaxy growth. It's still very broad. Now I'm going to show you a set of slides that I borrowed from the speakers at our conference, which starts with this wonderful graphic that Rachel Somerville showed. I think it actually goes back to Drummond Fielding, who was another great theorist in this domain. And they're analogizing the two science cases of HabWorlds here in a very meaningful way. What I just showed you was spectra of the Earth, or model spectra of the Earth over the course of its evolution. That's what we're calling here the circumterrestrial medium, where we have condensation into clouds, precipitation as rain, aspiration in plants, photosynthesis, percolation of water back into rivers and streams, evaporation into the atmosphere, and the whole thing goes around again. Well, galaxies have a very similar ecosystem surrounding them. They're not moving water around, really. They're moving hydrogen, helium, carbon, nitrogen, oxygen in its various forms, some of it very hot, some of it very cold. But you have a similar kind of idea that material cycles in and out over some very long timescales, and that circumgalactic medium is dominated by condensation and accretion and outflows. And then when it's in the galaxy, there's star formation, black hole formation, and feedback from those two things. So understanding the physical details that go behind the cartoon here is very much the goal of the unveiling the drivers of galaxy growth part of the science case. I really like this translation of that cartoon into a more detailed picture, which I ripped off from Chris Hauk, which shows two different versions of a face-on galaxy and an edge-on galaxy with, yes, these are cartoons, but they're a little more detailed in the sense that they show you what we're thinking of as the interaction between star formation and their supernovae and the feedback that bubbles up out of the galaxy disk that's labeled here, multiple supernovae in the bottom. The gas that gets ejected probably gets processed and recycled. Once it's in the CGM, it may fall back down after it's cooled and condensed again. And so the cycle repeats over the billions of years that galaxies are forming. So coming to grips with this complex process, which, as you can see in the lower right, is manifested not only in neutral hydrogen observations, but ultraviolet observations and X-ray observations you might make of the magnetic field, which is now feasible in some cases, and a whole bunch of other things. So this is where we want to get to in terms of understanding. I'm going to use a set of our own simulations that we've built here under the Foggy project. Foggy is figuring out gas and galaxies in ENSO, which is our galaxy formation simulation suite that Molly Peoples and I built here at Space Telescope. This image shows you how a galaxy, a simulated galaxy, looks very different as you tune through the ions or the diagnostics that you use to study it. So if you're looking at a galaxy in neutral hydrogen, everybody's familiar with what radio maps of galaxies look like. They look like disks. Sometimes you see the extended parts of the disk going out further, but often you don't. And then if you look at absorption lines or emission lines of particular ions that go up through the ionization potentials, you see that neutral gas turn into highly ionized gas. So what I have here at the bottom is what I'd call a phase diagram, which is just a density plot of temperature versus density in the gas. And as you go from the highest densities and the lowest temperatures up through the scale to the lowest densities and the highest temperatures, you can examine each of those different phases with these different ions. Now, this is singly ionized magnesium, triply ionized carbon, oxygen ionized 5 times, and neon ionized 7 times. And by the time you're at neon 8, you're at about 1,000,000 degrees. So this tells you that you need to use this full suite of diagnostics from the ultraviolet range all the way up through the X-ray to capture this multi-phase material that is the cosmic ecosystem. The classical way we do this, and this is something I've done a lot of over the last 2 decades, is to examine the spectra of quasars behind the galaxies we're interested in. So what you do is you go find a quasar catalog, which was, back in my day, it was Sloan, but now there's a lot more than that. And you hope that it's behind a galaxy that's interesting. And then you use the absorption in the spectrum of that quasar to work out what's there. Is it magnesium 2? Is it oxygen 6? Is it carbon 4? Is it neon 8 in some combination? And that allows you to work out the density and temperature and metallicity of that gas. So one of the first things that I think of when I think about HabWorlds is, what does it do for me? And one of the things it does for me is allow me access to much more numerous background sources. For every magnitude you go down in the quasar luminosity function, you get about 6 times more background objects. So this is a plot that Chris Hauck made that he showed in his talk that illustrates this using M87, which is a very nearby massive galaxy with a big honking AGN. With a 4-meter telescope, you get a few objects, and I think these are actual catalogs of quasars. But the deeper you go, the more you get, and so you can use multiple probes to do multiple experiments of the same halo. There's an amazing outflow that was detected in emission from this object called Makani, which is here I've put it about the same scale. It's a starburst galaxy, and the wind has been detected in emission. That's the map there. The really cool part would be able to do the emission and the absorption because they provide complementary physical diagnostics. And right now we just don't have enough background sources to do the absorption part of that experiment on a regular basis. So that's one of the immediate term goals, or one of the most obvious to me goals of HabWorlds for the kind of thing I would do. But why do we insist? Why am I making a big deal out of the UV? And this is something that will come up again and again as you hear me and as you view talks from our conference. Let's look at the time axis or the redshift axis and look at the density of background sources, right? Look at that redshift axis. Hubble barely has any sources beyond about redshift 1 or 10 billion years ago. But as we go to larger and larger telescopes, and this is right here about where we're now thinking HabWorlds would be, now you can push out to redshift 1, which gets you back into a more interesting part of the cosmic star formation history, a more interesting part of the balance between star forming and quenched galaxies, and a much greater density of sources on the sky. Now, we're probably not going to be building a 15-meter telescope at this point, but this was in the Decadal Survey report, so there it is. But I think you can easily see the growth in the availability of background sources that makes this absorption line spectroscopy case so compelling for HabWorlds. And it means you can cover basically the last 80% of cosmic time in the same way that we've done with Sloan, which is the very nearby universe. Another idea that is, its time is past due at this point is to apply intensively multi-object spectroscopy in the ultraviolet. This is a map of the M83 galaxy, which has been studied with Hubble in this fashion, where people take. I happen to have a pencil in my hand, so the pencil beam sight lines to individual star clusters, looking at the outflows of their star forming regions, what we call down the barrel measurement. If you can deploy a micro shutter array like the one on the JWST's NearSpec, for instance, you get the option of doing hundreds of sources in a single exposure by individually configuring these thousands of shutters, where each shutter might be just a couple of tenths of an arcsecond. So you're really closely examining the outflows, inflows, metallicity variations, star formation properties on very, very small spatial scales. We might also consider an image slicer like IFU capability. It probably would have a smaller field of view, but might also allow the kind of multiplexing that's proving to be so useful in other wavelengths. That data might look like this, but thousands of times over, where you get the classic absorption line measures of inflow and outflow source by source, but for thousands of sources. So another reason I'm harping on the UV so much, well, this will be a little clearer now. What we have here is an argument for why the ground doesn't work, but we know that. But if we evolve that, each of these little videos of our galaxy down to the lowest redshifts you can reach, what you find is that the ultraviolet gives you a huge gain in the range of cosmic time that you can explore. If we're limited to ground wavelengths, all of these features, the neon 8 line, the O6 line, the carbon 4 line, magnesium 2, and so forth, you're only seeing them at redshift, and so you're only getting a small portion of cosmic time. Lower redshifts than that, later times than that, you can't see them. So the UV is an essential element towards capturing this physics over a much broader range of cosmic time, including the present time. That's really, really important. How far it goes into the UV is a matter of study and debate. There's an argument for going further down than Hubble does. Hubble goes to about 1150 angstroms. That's kind of unfortunate. It's a result of the material that Hubble's mirror is coated with, the magnesium fluoride. And it would be great to go down further to 1000 angstroms or even to the Lyman limit, because that allows us to pick up many of these very powerful diagnostics in the rest frame UV, extreme ultraviolet, like neon 8, things like oxygen 4, oxygen 3, nitrogen 3, all of which probe different parts of that phase diagram. So if you're interested in this particular problem, the ultraviolet coverage and how far down it goes, there's a UV science interest group that Steve McCandless and I run that would very much like to hear your input on the science behind this question. So let's move away from gas physics and mostly away from the ultraviolet and think about sharp pictures. Think about spatial resolution and sensitivity. Here is a sensitivity plot that we made a while back during the LUVOIR study, which shows the angular resolution versus wavelength for nominal apertures. And Hubble, God bless it, after 33 years, is generally working at about 100 milliarcseconds or 0.1 arcseconds. JWST, it turns out, is about that good at the wavelength of about 0.7 or 0.8 microns. It's an exquisitely beautiful telescope. It's performing better than expected. And so its spatial resolution is Hubble-like, even at its shortest wavelengths, where it was never intended to be that good. But of course, it's diffraction limited at about 1 micron. And so it has about a 40 milliarcsecond PSF at that wavelength. But by shifting into the UV optical and building a 6 to 8 meter telescope, with HabWorlds, we can start to spatially resolve regions where even Webb can't do that at its best performance. So what we have here on the right is just 3 examples where we've simulated galaxies, stellar fields, and protostellar disks at different resolutions. And the effect of making the PSF smaller is quite dramatic. So some scientific demonstrations of that would be this. Oh, I should have said, when you have a 10-meter telescope, you resolve 100 parsecs at any redshift. That's the size of your PSF. And 8 to 6 meter will be somewhere in the range of 150 to 200 parsecs. Think about that. Your spatial resolution corresponds to less than 200 parsecs anywhere to the cosmological horizon. That happens because the expansion of the universe works out such that objects eventually become, as they recede, the angular size versus redshift relation turns over. And so you can actually get objects the same size appearing a little larger, and that means your physical resolution, you can set a minimum value, and it's about 200 parsecs for any redshift. I find that amazing. One example of what you do with that scientifically is you do a lot of stars. You study galaxies at the finest level of detail that you can. This is the beautiful mat from the FAT project, the Panchromatic Hubble Andromeda Treasury Program. This slide was borrowed by me from Ben Williams. And with Hubble, this is 414 Hubble pointings. It took them, months of time to do this map. And the limiting factor on most of their metrics for the star formation history or the chemical abundances or the abundance of dust is crowding in the stellar populations. So if you look in the lower left, Ben has an animation of the star formation history of Andromeda on a place-by-place basis, right? They split the galaxy up into these little spatial bins, and they took the star formation history in each bin from the color magnitude diagram they observe in that bin. And when it gets to about 2 billion years, I think 2 billion years old, 2 billion years ago, you can see there's a burst of star formation in the inner region that they have affiliated with a particular merger. You can see the star formation is very homogeneous at early times, but very inhomogeneous at late times. So it's a really direct measure of the star formation history across the disk of this nearby galaxy. The name of the game here is resolution, because you can't do this when the stars are too dense on the sky. You have to have resolved light to do this experiment. So with Hubble, with ACS, if you look in the upper left, they could only get to around 15 stars per arcsecond before the completeness got too bad. And you can only really pick out the brightest stars that are standing above the background. At fainter magnitudes than that, which here is around 26th, all the little fainter stars just blur into a continuous distribution of light, and you can't do this kind of measurement. So resolution is the name of the game. You want to turn what looks like the bulge of Andromeda into what looks like the outer disk of Andromeda, so you can do this star-by-star analysis. And it goes basically as the aperture squared, because you're looking at the number of stars per square arcsecond. So this science case would apply not only in the nearby local group, but with this technique, you might be able to reach M81, Sen-A, the Sculptor group, and look at the diversity of star formation histories across not only disky star-forming galaxies, but also red and dead giant ellipticals, galaxies hosting AGN, many kinds of dwarf galaxies, a whole host of real galaxies where you can do this star-by-star dissection would be a total game changer for this kind of measurement. This is moving on to a contribution we had from Kate Whitaker, which, this one probably is one of my favorite highlights of the whole conference. Look at this picture, which is a deep integration. It's actually not a very deep integration, but for web, almost every integration is deep. There's something very, very unusual in this picture. I don't know if you've seen this, but that galaxy there, they believe they've detected globular clusters around a redshift 1.4 galaxy called Sparkler now. Let's go back and see if you can pick out the globular clusters. There they are. Nobody expected to see globular clusters, almost 10 billion years back in the past with JWST. This is not a HabWorlds image, of course. This is not even a HabWorlds simulation. This is just saying what's the unknown that you get when you have a leap in capability? This was a leap in sensitivity in near infrared and a leap in resolution. These things were certainly not visible to Hubble. So this is a really great example of the serendipitous discovery of amazing things when you have the leap in capability. We don't know what that's going to be for HabWorlds, but since these things are, tiny, very small fraction of an arc second across, and when they're young, at least, pretty blue, these objects and things like them definitely provide an argument for higher resolution and UV optical sensitivity. Interesting conversation with Mike McDonald, who came to tell us about the complementarity between UV and X-ray measurements of gas in galaxies. His particular interest was in very massive galaxies, clusters, and the AGN feedback that drives them. But there's just a huge amount of complementarity between the kinds of UV measurements I was talking about and the X-ray measurements that an observatory like LINX would make. And it allows you to carve up this phase diagram of gas in a way that you can see almost all of it. The other thing that came from Michael's talk, which I loved, was his idea that what you really want is the sensitivity of Hubble's COS instrument coupled to a very large field of view, like the MUSE spectrograph on the VLT. And he called it COS MUSE, which I thought was great. Now, we're probably not going to use that, but the idea is great, right? Sensitivity gain, field of view gain, multiplexing all at the same time. This is the best idea we've had so far. This is the idea that is really going to drive the aperture, the sensitivity, the angular resolution, the degree of multiplexing, the wavelength coverage, the efficiency, and every other property of the system. This is the idea that really is going to drive this observatory to the next level. The problem is you haven't told us what it is yet. I've thrown out a lot of good things that people have talked about in recent weeks and months, and things going back, science cases going back to the beginning of this study. But we don't know if we have the best idea yet, right? We need to get engagement of people with new ideas at every level. What do you want to do? How is it going to work? How long do you need to integrate? How long does the telescope, how big does the telescope need to be? All those things are up to you. And that's really why we're doing this exercise, to get those new ideas fed into the system. You might find yourself asking that question, and we do have tools for you to that will help you to use that, answer that question for yourself. We have online an imaging ETC for the workhorse camera, and we have a UV spectrograph that's sort of COS-like and sort of Lumos-like, but really sort of combines the best of the LUVOIR and HabEx concepts. These are running now at those URLs if you want to try those out. And they will help you say, well, if I need to observe this quasar or that UV source or that star at these wavelengths, what's my really crude approximate integration time to signal to noise to source brightness level in the usual way you'd use an ETC for this hypothetical instrument. And you'll notice that both of these tools have aperture sliders. What that's telling you is how large is the telescope, how much light gathering power does it have, and is my science really a science case that requires the aperture to be larger than 4, 6, 8, 10 meters, because those decisions aren't made yet, and there will still be a chance for that later. I'll just note really quickly that there's a lot of technology going into this, and there's a lot of technology development happening now and ramping up. So for instance, the shutters that will do the micro shutter slit masks are in constant development, and they're being tested on a rocket experiment that Steve McCandless runs. And there's many other tech development items that you could hear about if you attended those different SIGs and SAGs. There's a lot of activity happening at the small mission level, CubeSats, Sprite, Aspera. The AstroSat is a good example of precursor missions that are proving some of the technologies that HabWorlds needs. And this is a really new model. I mean, these small sats, CubeSats haven't existed long enough to have contributed to the development of the previous flagships. So this is really a growth area for proving that missions like HabWorlds are actually feasible at a much lower price point. We're going to have heavy launch for this. There's no way around it. Webb was difficult to get to L2. Launching something heavy all the way out is a big deal. So it could be Starship, it could be New Glenn, it could be the Artemis rocket, the SLS rocket. What the heavy launch does for you is it gets you to L2 initially, but it also opens up the possibility of servicing like we've had with Hubble, which has renewed the observatory every 5 years and really given us essentially new scientific capability every few years. It's a model we weren't able to use with Webb because it was the first big thing to go to L2, and there's just no way to get there right now. But in a future where space travel with heavy launch is more routine and hopefully cheaper, we'll go back to that model. And hopefully HabWorlds will be this virtual mountaintop where you can upgrade the instrumentation every few years. I want to put in a very enthusiastic plug for multiple wavelengths. I've been talking about HabWorlds, which is UV, optical, and infrared, but I grew up scientifically at a time when I got to enjoy the results of all the original great observatories across all the wavelengths, and that is a scientific boon. You can see the whole electromagnetic spectrum laid out before you, and it really constrains your models a lot better than any given wavelength. These are just demonstrations of how that works with Hubble, Spitzer, and Chandra. In the future, what we're aiming for is not only HabWorlds, but the X-ray Observatory, called LINX now, the Far Infrared Observatory, that's been called Origins. And the combination of these things should be more powerful together than any one of them would be independently. So there is a SAG, a science analysis group, which is really seriously beginning its work right now. The leader of that is Grant Tremblay. And you can contact him for more details. There'll be messages about how to get involved in that. But its goal is to integrate the science cases for all the great observatories into one coherent pitch so that NASA and the community and the academies and the government understand why it's so important to have a fleet. If astronomers don't advocate for this fleet, it won't happen. We have to band together despite any arbitrary boundaries we might see in wavelength in the electromagnetic spectrum. We have to band together to make this happen. And I think Grant is typing away in the chat if you want more details on this particular group. I want to close out my time by showing you slides from Julie Crook, who is the superbly capable program manager for the Great Observatories Maturation Program at headquarters. And these are slides that Julie showed on the first day of our conference. And they're directly on point because they tell you what you can do. That was the promised upshot of this talk. This is the boilerplate. We know what HabWorlds is. We know what kinds of observations it might take. But the thing that's new this time is not only transformative science, but also the general approach to developing the mission. Everybody knows the travails that JWST went through, especially in the last few years of its development. And that experience, along with reflections on many of NASA's other very large projects, like the Mars rovers and human spaceflight, including stuff outside of NASA, outside of astrophysics, like DoD procurement for battleships and fighters and stuff. And the lessons have all gone into these particular studies. So there's the GAO report on assessment of major projects. NASA did its own large mission study report. And Julie she was not only directly involved in these things, but is now the person adapting those ideas to HabWorlds. The major difference is that this time around, NASA will mature all the technologies to the point where you can design the telescope around them and expect those technologies not to change. One of the binds JWST got into was that the technology items, like the MIRI cryocooler and the micro shutters and aspects of the sun shield, were still changing as they were starting to build things. And it became a very costly exercise to continue chasing that iteration until it closed. So the goal this time is not to do it that way. So Julie has this plan which feeds science into the architecture. Architecture means like the size, the segmentation, the basic design. Is it on axis or off axis? Feeding in technology to implementation. So we're right now at the earliest phase of this. NASA has convened a group called START, which is the Science and Technology Architecture and Review Team, that has a central committee of astronomers who have been selected. We are waiting for them to be announced. We're right in the period between their selection and their announcement right now. The goal of the START is to quantify all the science cases. And I've given you many examples, but they were just examples, right? So we need to turn those using our tools into quantified yields, depths, times, performance, and all those things. The START's goal then is to draw lines that say this is the minimum science that we need to do, and here are the metrics that go into that. And if you change the design, how do those metrics change your science yield? So START's goal is to couple the science to the architecture in a very quantitative way. An example of quantitative is those tools I showed you a little earlier. Down here in the lower right, and I found the most obnoxious animation I could. This is your avenue into START. If you're not selected for START itself, which only has about 15 people on it, then you're part of what Julie calls the global START, the super START, which is the union set of everybody who's interested in this project and wants to do science with it. So you have several routes to that. You have this group, the Galaxies SIG. You have all of the fundamental PAGs, depending on your interest, but most of us would be co-PAGers, Cosmic Origins Program Analysis Group. There are routes for folks from abroad who aren't formally affiliated with US institutions to join in ways that are still being worked out. But in the structure of the global START, the PAGs, between the PAGs, the working groups, and these other avenues, everybody's welcome. So by this time, everybody should know whether or not they were selected for START. If you weren't, this is your route into this project. And there will be many, many, many friends there to help you. We have tools. We're going to have even more of those. And there will be announced ways to get involved in the global START. Probably within the next week or so, that will start. Those details will start to emerge. The stated goals for START are things that really have to be addressed soon. It's what are the science questions? What are the observations needed? What are the capabilities required? And to really quantify, as I said, the connection between the science and the architecture. HabWorlds is already the most maturely developed concept that a decadal survey has ever evaluated. The HabEx and Louvois reports ran to hundreds of pages of appendices, and it went as far as producing a master equipment list of all the parts, right? It was very far advanced compared to other decadal surveys, which means we need to work even further to continue to advance the concept in great detail and to quantify all the things we need, because there will be a time when some of the engineering side comes back to us as scientists and says, I can't do that. And they'll also ask, what can I do if I can't do the thing you asked me to do? What's our second best option, or how does this affect the science? And we have to have scientific answers to justify those engineering trades, or those engineering trades will be made in a way that might not help the science. So the scientists have to be there to protect. That means mapping all the different science cases to all the different capabilities. It's complex, but we have the information we need to begin on this. That's one of the things START will do. Is that going to loop? What we hope START will do is that by 2030, or hopefully even earlier, 27, 28, the review that the decadal, the so-called gate review that the decadal has mandated to proceed to a real project will have been passed. Be ready with technology, ready with science traceability, the quantification of science versus architecture I was just talking about, and be ready to start. And from that point, NASA's idea is to try to build this to a fixed schedule that's like a planetary mission, right? Planetary missions, they launch them or they don't. If they miss their window, that's it. They don't get to go because they're not going to get to Jupiter in time. So there's the idea here that schedule will be considered a high-level requirement. And for that to succeed, all this maturation part, which happens between now and about 5 years from now, is the critical time when the science input is most important. This is the time when all the scientists, all of us, have to be sitting with ourselves and with the engineering side of the equation saying, what's possible? What can we do? What do we really need versus what we just kind of want? All those decisions are going to be made in the next couple of years. So that's why we need your help. I remind you, the best idea we have for this is the one you haven't given us yet, as I said earlier. So please view this as an opportunity to influence an observatory that you'll use and your grad students will use and their grad students will use and so on down the line, hopefully for decades. I'm done. So thank you very much for your attention. I suspect there might be questions, so I will stick around and we can talk. Thank you.
How do I applause? Here, this is how I applause. I forget how in whatever system I am. That's fantastic. This is I love all the graphics. I will say that I'm a graphic aficionado. So this was fantastic. There were several that I really want for class, really, if I could.
Most of these were either I made them and I circulate them, or other people made them and gave them in talks. So I think for the most part they're available if you'd like to.
That was an aside. I was opening the floor to questions from people. Let's see if I can. Do we have any raised hands?
Some questions out there,
or just pop in. I have questions, but they are specific to my interests, so I would like other people.
Nothing wrong with that.
Okay. I have one that's been lingering for me for the quick QSO stuff. You had a plot. The number of every magnitude deeper, 6 times more sources. That was Chris Hawkes's plot. Mm-hmm. Is that per a particular area, or is this the entire sky? How is that?
Yeah, I've given that on a per area basis. So, but if you multiply by the entire sky, it's the same factor because it's a ratio of number of objects at this magnitude limit versus number of objects at that magnitude limit.
I was kind of
obviously
curious.
That's not true as you get close to the galactic disk because there is the zone of avoidance, but at high latitudes, it's basically every magnitude you go deeper, you get about 6 times more objects.
So would radio catalogs be any improvement there or quite the opposite?
I mean, only a fraction of them are radio loud, but it does help. There have been instances where objects that were in the radio catalogs, but behind the galactic disk, or dust extincted enough that it was hard to pick them up in the UV, were then identified. That factor of 6 is at the UV wavelengths where I'm describing these measurements. I think it's kind of different because of the way the colors of spectra of quasars works out. It's not a factor of 6 at the other wavelengths.
It's sort of a do we have these catalogs on hand? That was the question I was working up.
Oh, yeah. Oh, I see. Galax itself is deep enough to get you to 21 almost. Okay. And that's about, I made my bones with Hubble observing 18th magnitude quasars with COS. So another 3 magnitudes is plenty.
Okay. I mean, it's the kind of thing where we're getting things like these UV pathfinders might get us the catalog. It's more of the catalog will exist or is already in existence. The other thing was I saw a Gaia catalog go by, and I was wondering if that was enough for.
Those would have to. You need to know the UV flux to really reliably use it in the ultraviolet spectroscopy. But any source of the quasars is fine with me as long as I know how bright they are in the UV.
My question is always like, do you have your target list? So if Habitable Worlds pops into existence tomorrow,
I have my target list.
Okay.
I have my target list. But another possibility is that if you push the sensitivity of this thing deep enough, you can start to use background galaxies, which are another order of magnitude denser on the sky. They present other problems. They don't have flat, beautiful synchrotron spectra, but they're still pretty good.
I'm aware of the use of background galaxies. That was my PhD. But so
of course.
Does anyone else have a question? I mean, I'm going to open the floor again. Please jump in. Otherwise, I'm going to hog the speaker, which is not what I want to do.
I see Aaron. Aaron has a question, Aaron Smith. And then Stephen, you can go next.
Hi. Yeah, so great talk.
Well,
I'm just wondering, how important is the optical and infrared components to this mission? Is it like, the UV is really the strong arm and we tag along the others for systematics, or?
oh, no, definitely not. I mean, I put a lot of emphasis on the UV. Partially, that's my own scientific bias. Second, it's where the more challenging requirements are laid. So an optical telescope is, in some sense, the easiest part of this, technologically, design-wise, construction-wise. So I'm focusing more on things that drive the requirements away from the easy part. But this science case here, it spans all the way from the near ultraviolet to the near infrared. So you see Ben has said here down to 0.2 microns, 2000 angstroms, I would say. But it also goes up into the optical F814W 475. The other reason you need it's a little bit self-serving too, I guess, but the other reason you need the optical is that that's the UV, but redshifted, right? And that's the argument they made for JWST. It's the optical, but it's redshifted. So yes, this is definitely about all the wavelengths between probably 1,000 angstroms out to where the thermal emission from the telescope starts to be debilitating, which is around 1.7 microns.
Thank you. And Stephen, you can go.
Yeah, Jason, I missed the first part of your talk because I was teaching class, but the problem of quasars, that's a great leap that a 6 meter would bring to us, in terms of an expanded capability to really grow IGM and the ISM. Can you think of other areas where there's a similar, huge leap in capability, aside from just the total number of quasars that you have available?
I mean, there are resolved object metrics that goes d to the fourth because of the surface brightness and scaling with aperture. This particular case is pretty groundbreaking. And if you didn't, I don't know if you were here for this one, but I mean, when I first saw these globular clusters around this redshift 1.4 galaxy, I said, no way, right? There's just no way. But there they are. And this was a total surprise. Maybe somebody somewhere should have been creative enough to say, hey, I bet we're going to find globular clusters around redshift 1 galaxies, but nobody did that. So, the element of surprise you get from the combination of area and depth and resolution is kind of hard to guess, right? And it's hard to predict. And I would use this as a great example where we need everybody out there thinking in advance, once I have this resolution, this, nearly 10 milliarc second PSF or access to 30-second magnitude, what can I do with it? If you look at this, this is another plot that drives that home. And I have I deliberately set the ETC values here to be, let's see, the imaging ETC calculation there is 30-second magnitude with an aperture of 6 meters and a 10-hour observation. And this shows you that, for the typical signal to noise you would get in a good imaging observation around 30-second magnitude is in the conversation. So that's a big leap.
Thanks.
Great. Any other questions? If not, let's thank our speaker again.
Coming up on the hour. Does anyone have any more questions for?
I will make these slides available and to Benny and Aaron.
And also slides from the conference in June, right?
Yeah, the July slides are all, the talks are all online, and I put in a QR code there. Somebody probably dropped a link in the chat. It's not hard to find. It's on the Institute's webcast archive page. Google will find it for you. There's a lot of excellent material. I only got to draw from maybe half a dozen of the great talks, and there were 40 of them. So check it out.
Yep, I'll get all the information and put it in one announcement along with the recording of this talk when it becomes available. So come back in a month. So we have, thank you, Jason, for kicking start this seminar series that goes in the next year. But really, we come back every first week of the month on Tuesdays. So next month, we're going to hear from Aaron Smith actually on some simulation perspective of what we can do for HabWorlds. All right, so everyone have a few minutes back, if you like back. I'll see you next month.
Take care. Bye.
Bye.